Hello and welcome to my to the second in my series of videos. First one was on Young's double slit experiment. I will refer back to that a bit later, but this one, of course, as you can see, is on quantum entanglement. And what we want to do is talk about what quantum entanglement actually means. Very, very simply, if you want far more involved information on what quantum entanglement is, how it's measured and so on, how it's tested, there's a lot more stuff on my blog. Also, of course, it's all over the internet. There's lots of very reliable places you can go on to get information on quantum entanglement. But essentially, this is what it is. That's a small illustration that you see there before you. And so to start off with this, there's the source atom. Now that would be situated somewhere here. What it is some kind of crystal that we can excite and get it to produce two particles. Let's say we're working with photons. We'll stay with photons. We stayed with photons with the double slit experiment. We're going to stay with photons here for the moment. So this source atom is so excited that it produces two photons, both at the same energy level from the same atom. Now, what we'll do, what happens is with these experiments on quantum entanglement is that the photons are produced, and then one is looked for over here on the left, the other one is sought out on the right here. And when we find the one on the left, you'll see it is polarized in this particular direction, and then we look at the other one that's gone off in the other direction and it's polarized in the opposite direction. Now that would be so because these two photons have come from the same atom at the same energy level, and you can't have two exactly the same particles existing in the atom together. They've got to be different in some ways. So we'd say for the photons, one's going to be polarized in one direction, the other one's in the opposite direction. Now this distance between one and the other could be any distance, could be 1 million miles. Let's keep it at 1 million miles. It has been done over quite some distance. All of this has been done over some distance across islands in the where were the islands? I think the Canaries, if I remember rightly. You can look that up, but very convincingly done across these vast distances. So what happens is we look at one, say this one on the left here, it is in that direction. We will know that the other one is in that direction. It's polarized in that direction. And so far, quite simple. When they left the, as Einstein had it, when they left the source atom, it was already decided that this one on the left was in one direction and this one. So the two went off in their different directions. Okay, no problem. And Einstein likened it to a pair of gloves. If you had a pair of gloves and you separated them by 1 million miles and you put the left hand glove in this left hand place, as soon as you opened it you would know that you've got the right hand glove 1 million miles away. Okay, no mystery at all. Very simple. So let me just take these marks out now. And the questions on this system started when it was proposed that there was no no fixing of the polarity, no fixing of the polarization from here, that the polarization may not be determined until we measure it, and when we do, the very measurement fixes it in this direction. But when we measure it, then we know that the other one will take on the opposite direction. We know that. But if they weren't fixed already from here, how can this one on the left tell this one on the right which direction to go in? Einstein hated this idea that no matter what the distance, these two particles remain entangled, remained in a way in communication with each other. And he called it spooky action at a distance. Very famous quote. And so the discussion went on, and you weren't able to do these, to experiment on this to any great extent, because technically you didn't have the equipment to do it. But as time went on, it got closer and closer to being able to do these experiments. And before they were able to do them convincingly, a very clever physicist called John Bell devised a mathematical system, which was a set of inequalities that just say A is greater than B. It's not nowhere near as simple as this, but in essence, he devised around saying, if you could do this experiment, if you could get enough, do it enough times that you could get enough results, if you collated all your results, if A was greater than B, in other words, this inequality was so, then this was fixed beforehand. There would be hidden hidden local effects that would fix them. However, if this were not so, if it turned that B was greater than A, then the result would be that they're not fixed until we look at them, one then the other. So that some very famous experiments were then done. The results collated, and Bell's inequality applied to this, and invariably A was not greater than B. Invariably, the experiment showed that the polarization was not fixed until this point here. As soon as we fix this one takes the opposite across our million miles. How can it be? Okay, very mysterious, still remains a mystery. What I want to do is offer an explanation. And it's very much to do with, if you were to look back at what I did with Young's double slit experiment, the way to make real sense of that is to understand that photons, staying with photons for the minute, photons do not have independent existence. That when we excite this crystal, the atom that's going to produce these entangled photons, we have to look at this from the point of view of the photon itself. From here to here, 500,000 miles, doesn't make any difference as far as the photon's concerned. It's a so-called massless particle. Distance, time and distance doesn't exist for it. This is instantaneous, and so is this. The photon never leaves the source atom. It is produced, it's the energy level in the source atom. And the Pauli exclusion principle means that in that source atom, if we create a pair of entangled photons, one will be polarized in one direction, one polarized in another, because they're both at the same energy level. It's the energy level of the source atom that those things exist, and the polarization isn't determined in there. It's just fully energized. All that happens is, over here on the left hand side, we have a receiving atom that is open to receiving energy, and it will receive the energy at this this polarization, and basically just about at the same time, over here, because this distance as far as the light's concerned doesn't exist, then this one will take the rest of the available energy in the other direction. That's it. All this stuff about it not being determined until we look at it, it's led to a whole lot of fairy tale physics saying that somehow or the other it's dependent upon our consciousness to make these things happen. No, this stuff is happening all the time. Even if we didn't exist, this would be happening. So that we look at it from the outside. Of course, across the million miles, there is a time difference. But the time that this is taking on the energy and the time that this is taking on the energy, as far as the source atom is concerned, is exactly the same time. It's instantaneous. It's only us looking at it from the outside across that distance. We know this from Einstein's special relativity. There is a time. across here. But they're not communicating with each other. They're just taking the available energy from the source atom. That's it. Summarize this quite simply again. It makes sense, and it's explained when we realize that photons do not have independent existence. They don't exist outside an atom. And it's atom to atom communication that we're experiencing. You can't look out in space and see photons flying everywhere. You'll only get photon effects on materials, on other atoms when they appear in space. Other than that, space doesn't have photons in it. It's empty. You've got to have receiving atoms. So the sun is a ball of nuclear reactions, and the atoms in the sun are splitting, not splitting, joining up and so on. It's not splitting, it's joining together and releasing energy, and the energy isn't released in the photons are not coming out. They're there. The resultant let's say hydrogen forming helium in the sun gives a helium atom that is very excited, and it wants to put its extra energy somewhere, and it looks around throughout space. There's no distance as far as the photon is concerned. It looks to Earth. Yep, there is an atom on Earth, might be part of you, and straight away that energy is transferred. Of course, to us, there's a time difference. And you're going to feel it in the form of heat. You're going to see it in the form of light, because some of it will be reflected, some of it will be used as heat. That's it. So, we're able to explain this. If we then look at this in terms of electrons, now the electrons are a bit different. The electrons will take some time. And they move at almost the speed of light. Why do they move at almost the speed of light? They have mass, apparently. They're not massless particles, therefore they move through space, apparently. But it makes no difference. I still say that the electron itself... Now, I will do a video on the difference between photons and electrons and so on, but the electrons will have spin in one direction, spin in another direction. So spin up here means spin down over here. There is a time lapse as far as the source atom is concerned. It's very small between here and here across the 500,000 miles, but it's the same time lapse here across the 500,000 miles, so that we still see this as a whole big time lapse. As far as the electron is concerned, it's hardly anything. So it doesn't make any difference. The photons and the electrons do not have independent existence. It's our perception that's got this. This is a different definition of what we're seeing. All of the mathematics, everything that we've built up to explain all this still applies. But in this definition, with these particles, subatomic particles, not having independent existence, then these things start to be explained away. Let me just clean it up again. As I said, and I hope that makes sense, a whole lot more information on my blog, as I said. I plan to do my next video on the photoelectric effect, but as I say, I will be doing one on the difference between photons and electrons. But so far, I hope you can see that all we've got is a very simple definition of what's going on that explains away the deep mysteries in Young's double slit experiment and quantum entanglement, and I will go on and explain away almost all of the problems, the unknowns, the mysteries that have led to fairy tale physics. So I hope you'll join me in the next video. Thank you for being here.